Okay, briefly want to touch on phase shift and sinusoidal curve fitting. And this relates back to recording number 9. If you're dealing with sinusoidal type of models, then they're going to fit the structure, and this is the way the book is laid out, the general form. They use those symbols. You can use A, little a, B, C, D if you chose to. You can use any symbols you want there. The transforms is what are critical. Okay. If you play the transform game like I've illustrated in a previous example earlier, we could move the A and the B over to the other side. And in a similar fashion inside here, we could take that angle, omega t minus phi, and we could write it in this kind of a structure. This is the y stuff, is the way I refer to it. And then inside here on our sine function is going to be what's called the x stuff, or the stuff related to the angle, in this case t, angle t. So if I factor out the omega using some algebra, and you can go back to recording number 9, I think, to see the details on that, this would become t minus phi over omega divided by 1 over omega. So if this A value down here has applied some vertical stretching or squeezing vertically, or maybe even turning the darn thing upside down, then over here on this information related to the angle inside this sine function, then you should expect to see this multiplying transform factor 1 over omega doing something similar to what you see here, except on the independent variable. So that's going to cause it to be stretched out like a piece of rubber band, maybe, or squeezed in like an accordion, or potentially even turned around the y-axis. Really simple illustration of this is, what if you were asked to do this? This one. This is like an f of negative x. And all that does is that's essentially just the sine of x over negative 1, if you want to think of it in terms of what I've just done up here. And what this causes to occur is the graph to get turned around the y-axis. So the graph of this thing right here would be a sine function that looks like that instead of the traditional one. Okay? All right. And the period has been altered either by stretching or squeezing horizontally, hasn't it, by this multiplier. So the period of the sinusoid is going to be this 1 over omega times your fundamental period. And there's that formula we had earlier, 2 pi over omega. Okay. This thing right here is analogous, phi over omega is analogous to this value b. B, you know, look back up here. B is what you're familiar with of causing something to be either the whole graph function to be lifted up on the picture or shifted vertically downward. Over here, you're going to expect to see that thing kicking the graph either to the right or back to the left. And that thing is called the phase shift. That's your phase shift right there. Okay. If you need to review, this is just the generalization here. If you need to review, please go back to the recording number 9. Or come see me and I can work with you individually on it. All right. Let's go back. Oh, and then also just for reference purposes, if you still, I didn't actually write the page number of that section down in the book, but you can find it. Let's go on to chapter 7 and see if we can get a little further along here today. In 7.1, we start talking about inverse, sine, cosine, and tangent functions. I'm not going to go back through the whole story on that. What you need to be aware of is you take your original, and I've given you this numerous times, and you can find it on the recordings. This one would be, I think, numbers 10 and 11 on the recordings. If you take a sine function and don't let it go past its crest, and don't let it go past its trough, to the right and left on a sine, then that thing is 1-to-1, passes the horizontal line test. So when you form the inverse, so here's your sine x graph, then passing a horizontal line test, if you then take and interchange x and y, the independent variable and dependent variable, then you're going to get that, you're going to get a graph that ends up having a range that was the domain over here. That's going to become your range. And the values in the range over here from -1 to 1 are going to become the domain here. And the graph of that thing looks like this. This is your inverse sine function. Inverse sine function. Okay? All right? Okay. With that in mind, then, what you can do is you can think back to your unit circle, and you can see on your unit circle that the range of angles allowed here is from -π/2 to π/2. The inverse cosine function in a similar development would be using this much of it from 0 to pi and a range from 1 -1 to 1, and then you go through the transformation to form the inverse, and you're going to end up with a graph that starts here and wants to wiggle its way up the y-axis as high as pi and as low as 0, and from -1 to 1 on the domain. You've seen this before. And on your unit circle, that covers angles from 0 to pi right here. If you have trouble with the inverse trig functions, oh, and then the inverse tangent I better throw out here on the board as well. Let's do that, and then I'll address how to handle it if you're having confusion about how to deal with these things. So the inverse tangent, you have to think about your tangent function, and a tangent through the traditional single cycle from its asymptote on the left to its asymptote on the right, looking like that, forming its inverse is going to give you a graph that's going to have horizontal asymptotes up at y=π/2 and as low as y=-π/2. And it's going to look like this. Domain becomes range, range becomes domain. Okay. So there's your inverse tangent function. Okay, now I had a variety of problems to go through with you on this, and I think we have enough time to get through them if I do it quickly. Just a closing picture on this guy is you can see the range of angles again. It matches what was available for the sine. And notice that this captures all the possible tangent readings, from -1s to +1s. But the restriction on angles are between -π/2 to π/2. Right? So, here are a couple problems. Number 41 on page 451 asks us to evaluate this exactly. Inverse sine of the sine of 9π/8 equals what? You're going to be real tempted to simply say the answer is 9π/8 because an inverse function and a function will essentially undo each other if this value is in the range of this function here. That's the hard part for people to grasp. So the way I handle these things is I always work them from the inside out. I work them from the inside out. I go back and probably think, I could think of my basic sine function as a graph. And where am I? So let me show you both. So if I'm at 9π/8, I'm right over here, aren't I, on my unit circle? Just 1/8 of pi past pi. And the sine sitting right here is this value. So that's that internal part is sitting right there. Now what you observe is if you go back over on your unit circle, back over here into the fourth quadrant, you can see that same sine reading. This height, that y reading there, is identical. And that angle would be at -π/8, wouldn't it? Okay. Come over here onto your sine function. If you're at 9π/8, here's pi. If you're at 9π/8, you're right here, a little bit past pi. There's that sine reading, folks. Where does that show up back closer to the y-axis here? Back over here, doesn't it? Same y reading right here. And look at the symmetry. Because of the symmetry of your sine function, past pi/2 by 1/8 of pi means you'd be passed off to the left here at -π/8. I think I may have said that not quite right, but the picture is correct. See it? See the math? So what you're going to answer then is you're then asking for, here's something I said in the previous recordings, is when you see an inverse trig function, think angle. You're looking for an angle in this problem. The angle has to be in the range of what's allowed for this function. So what you have to do then is come back and identify that as being -π/8, which is illustrated here and here. And you go back over there on the restricted range of angles from -π/2 to pi/2, you have to be in here to be able to pick up your answer. So the answer to that thing is -π/8. I have time for one more real quick one. Number 66 on page 451 also, I believe, if I can read my writing. It says solve. And it says this, -4 inverse tangent of x equals pi. See, the result here, folks, look at this for a second. This thing has to be an angle. This mess here has to be an angle. So we need to solve this. So the inverse tangent of x is equal to -π/4. And here's the little trick I wanted to point out to you, is if you ever have trouble with these inverse functions, what you can do is rewrite this statement. Because the angle is -π/4, and it happens to have a tangent I'm sorry. I wrote that wrong. The angle is pi over 4. X is the ratio. So x must be the ratio that happens to have a tangent that is the tangent of minus pi over 4. And then at this point, you then come back to your unit circle because minus pi over 4 is familiar to you. And you answer the question. What's the tangent reading right there? It's the slope, isn't it? -1. So x is -1 on this problem. Okay. So on the review, I didn't get as far as I'd hoped to today. I only got up through section 7.1. And what we'll do in the next session is we'll try to go through as far through the rest of the course as I can on a review tomorrow. Okay? That'll do it.